We're talking about right now. Well, I mean, I don't, but like, you have what you mean. I've done the question like 3 times.
Okay, today we are going to solve a few more problems together. So let's look at this middle one. We have a refrigerator. We have this refrigerator. It has two thermal energy reservoirs. One is at low temperature. The other one is at high temperature. And we transfer heat from this low temperature thermal energy reservoir, which is the refrigerated space, for the amount of QL, and transfer this heat to high temperature, this high temperature thermal energy reservoir, for the amount of QH. And to run this refrigerator, we need to provide work, W net. If we use rate form, we can add that on top of it. Then the energy balance equation is W dot net is Q dot H minus Q dot L. And we can evaluate the performance of this refrigerator by using COP, coefficient of performance, or beta of refrigerator, can be determined by the desired output, which is the rate of heat transfer from this refrigerated space, divided by the required input, which is this net work, W dot net. So that's how we can evaluate the performance of this refrigerator. By the way, this W dot net is the same as the difference in the rate of heat transfers. So we can say Q dot F over Q dot H minus Q dot F. So this is how we understand refrigerator system. Then let's solve this problem. We are going to cool water from 23 degrees Celsius to 5 degrees Celsius. So this is related to Q dot L. The heat rejection, the rejected heat in the condenser is 570 kilojoule per minute. So this is Q dot H. So Q dot H is this one, 570 kilojoule per minute. Then, if we convert the unit to kilowatt, 1 minute is 60 seconds. . we can cancel minute, then we get 6 point, what is it? Not 6, 9.5, 9.5 kilowatt. That is Q dot H. And the power consumed by the refrigerant system is 2.65. So this one is 2.65 kilowatt. And we found Q dot H is 9.5 kilowatt. So you can determine the rate of heat transfer from the refrigerated space, which is Q dot L. This one is 6.85 kilowatt. So we can remove heat from the refrigerated space at the rate of 6.85. So this heat transfer is going to decrease the temperature from 23 down to 5 degrees Celsius. Then, how can we determine the rate at which water is cooled? In other words, the volumetric flow rate of this water. We can first calculate the mass flow rate of water, and then divide by the density of water, which is 1 kilogram per liter, to determine the volumetric flow rate. So let's do that. This Q dot L can be determined by m dot times specific heat times temperature difference, which is 23 minus 5. By the way, if you are not sure how to get this equation, this evaporator is a heat exchanger, so you can use the energy balance equation for heat exchanger. If you don't remember, you can start with the energy balance equation, the general energy balance equation, Q dot in plus W dot in plus M dot at the inlet. This one has enthalpy, kinetic energy, and potential energy. It's going to be Q dot out plus W dot out plus M dot at the exit. This one has enthalpy, kinetic energy, and potential energy. Then for this water, we can neglect kinetic energy change and potential energy change, and there is no energy transfer by work. What about this work? That is the work to the refrigeration system. We are talking about water in the evaporator. So this one is for water. Then there is no energy transfer by work. What about heat transfer? Heat is removed from this water. So we have Q dot out, which is this Q dot L. And there is no heat transfer into the water. And there is only one inlet and one exit for this water system. So you can remove these subscripts. So we have the rate of enthalpy at the inlet, the rate of enthalpy at the exit. So if you move this one to the left-hand side, then the equation is Q dot L, this one is M dot H in minus H out. Then how do we determine H in minus H out? If you have water as your system, you can use specific heat. So this is M dot times specific heat times T in minus T out. So this is shown right here. Okay. So we can use this energy balance equation for this water system in the refrigerated space to get this equation. Okay. Then the rate of heat transfer is 6.85 kilowatt, and specific heat is given 4.18 kilojoule per kilogram degree Celsius. What is the temperature at the inlet? 23. Temperature at the exit? 5. So 23 degrees Celsius minus 5 degrees Celsius times m dot is 6.85. So can we determine the mass flow rate? Yes, we can. So from this, the mass flow rate m dot of water is 0.09104 kilogram per second. Now, we want to determine this flow rate in liter per minute. Liter per minute. So liter per minute is volumetric flow rate. M dot can be determined by density times volumetric flow rate, and this one should be in liter per minute. Then what is the density? The density is 1 kilogram per liter. So this one is 1 kilogram per liter. So we have kilogram, kilogram. If you move this density to the right-hand side, what we get is 0.09190 liter per second is V dot. And we want this V dot to be liter per minute. So you can multiply this by 60 seconds is 1 minute. Then you can cross second. Then you get 5.46 liter per minute is the volumetric flow rate. So that's how you solve this problem. And the other question in the problem is the COP of the refrigerator. Then we found Q dot L is 6.85. This one is 6.85. So you can determine COP. That is 2.58. This is how you solve this problem. Any question? The last problem is this one. We have R134A enters the evaporator coil. Evaporator coil is placed in the refrigerated space. So we are talking about Q dot L in this case. So let's solve this problem. At the back of the freezer section, so we have a refrigerator. this refrigerator has two thermal energy reservoirs. One is at high temperature. The other one is at low temperature. So this is the refrigerated space inside of the freezer section. And outside is going to be, the kitchen, right? Kitchen air. And heat transfer direction is from low temperature to high temperature in the rate of Q dot L and Q dot H. To make this happen, we need to provide work. W net. W dot net. So this is a refrigerator. And to evaluate this refrigerator, we have two equations. One is the energy balance equation. W dot net is Q dot H minus Q dot L. And the other one is COP of this refrigerator. In other words, beta can be determined by Q dot L, which is the desired output, over required input, W dot net. We have the information at the inlet and the exit of this evaporator. So in the evaporator here, the inlet, I'm going to say inlet is number 1. So P1 is 100 kilopascal. And quality X1 is 20%, which means this is a phase change process number 3, saturated mixture. So this is the inlet. What about exit? At the exit, pressure is 100 kilopascal. And the temperature T2 is minus 26 degrees Celsius. So heat is removed from this refrigerated space. Then where this heat goes into, this heat is going to be observed by the refrigerant in the evaporator. So this Q dot L is going to be heat transfer into this refrigerant. So Q dot in for this refrigerant is going to be Q dot L in the refrigeration system, right? So, and we know the compressor consumes 600 watt. So this one is 600 watt. And the COP is given. COP is 1.2. Then we want to determine the rate of the refrigerant and the rate of heat rejection to the kitchen air. So let's do that. We can solve this B first. COP is 1.2, and we know the power is 600. So this power is 600 watt. COP is 1.2. Then what is Q dot L? 720 watt. Then if you know W dot net and Q dot L, can you determine Q dot H, which is the heat rejection to the kitchen air? Yes, we can. So this one is 720. This one is 600. So what is Q dot H? So from this, Q dot H is going to be this one plus this one, 1320 watt. This is the rate of heat transfer from the refrigeration system to the outside, which is the air in the kitchen. Then let's determine the mass flow rate of the refrigerant. So to determine the mass flow rate of the refrigerant, we need to come up with the energy balance equation for this refrigerant. So let's find out what is the energy balance equation for this refrigerant. If you don't know, you can start with the general energy balance equation for steady state open system. Q dot in plus W dot in plus M dot at the inlet, which is number 1. This M dot has enthalpy, kinetic energy, and potential energy. It's going to be energy transfer out of this control volume, which is Q dot out, W dot out, plus M dot at the exit. Exit is number 2. This one has enthalpy, kinetic energy, and potential energy. We can first neglect kinetic energy change and potential energy change because this is a simple heat exchanger. And there is only one inlet, one exit, so you can remove subscript for M dot. And there is no energy transfer by work in the evaporator. This W is work goes into compressor, goes into the compressor of the refrigerant. We are talking about this evaporator. So there is no work. And we have a heat transfer into the refrigerant because we are absorbing heat from this refrigerated space at the rate of Q dot L. So Q dot L is Q dot in. So this one is Q dot in. There is no Q dot out. So we have the rate of enthalpy at the inlet, the rate of enthalpy at the exit of this evaporator inside the freezer section. So the energy balance equation is going to be Q dot L is going to be, if you move this one to the right hand side, M dot H2 minus H1. Then do we know Q dot L? Yes, 720. What? Can you determine H1, H2? Yes, because we know, the pressure and the quality at the inlet and pressure and temperature at the exit. So it's like a simple table problem again, right? So let's look at this one. We have a phase change process number 3, saturated mixture. If you want to determine its specific enthalpy, we can use linear interpolation. So H1 is HF plus quality X times HG minus HF. Then we already know the quality X, 0.2. Then where can we find HF and HG? From the given condition. What condition do we have? Pressure, 100 kilopascal. So we can find HF and HG at 100 kilopascal. We have a pressure table, table A11 at 100 kilopascal. HF is here, HG is here. So the numbers we are looking for is this one and this one. So HF is 16.29, 16.29. HG is 231.35. So from this, we can determine H1. If you do, we get 59.30. That's H1. What about H2? We have pressure and temperature. Then can you determine H2? Yes, but we need to know the phase change process. So let's do that. We can use this pressure to make a TH diagram, and we can determine the phase change process. TH diagram looks like this. And pressure is 100 kilopascal. To complete this TH diagram, we need to know T set, HF, HG. Since we know temperature, if we determine T set, I think we should be able to determine the phase change process. So what is T set? T set at 100 kilopascal is minus 26.43. Minus 26.43. Excuse me, degrees Celsius. So what is the temperature? minus 26. Minus 26 is greater than minus 26.43. So slightly above. So what is the phase change process? Number 5, superheat vapor. And once you know it is superheat vapor, you can go to superheat vapor table. So where is it? Here is 100 kilopascal. The first row is the saturation temperature, which is minus 26.43. The second row is minus 20. Third is minus 10. And what is the temperature at the exit? Minus 26. Between these two numbers. And we want to determine H between these two numbers. So what we need to do? We need to do a linear interpolation to determine H. Then let me show you how we do the linear interpolation. So the left-hand side is temperature T. The right-hand side is specific enthalpy H. The lower end of the temperature is minus 26.43. And the upper end is minus 10 and minus 20. The corresponding H value is going to be 231.35 and 236.54, these two numbers. Then, what is the temperature at the exit? Minus 26. What is the enthalpy H? I don't know, so it's just H. Done. This one goes up, minus 20. This one goes up, 236.54. So can you determine H? Yes. If you do the calculation, you get H2 to be H2 to be 231.7. That goes to H2. So in this energy balance equation, now we know everything on the left-hand side, 720, and we know H1 and H2. Can you determine M dot? Now, yes, you can determine M dot. So if you do the calculation, M dot is 0.004176 kilogram per second. That's how you determine the mass flow rate of the refrigerant. Any question about this problem? So that's everything about how to evaluate the performance of 3 cycles: heat engine, refrigeration system, and heat pump. That was the first half of this chapter 5, and we are talking about the other half. We are going to study Carnot cycle, which is the ideal cycle. So to study ideal cycle, we need to, learn a little bit about reversible and irreversible process. So first, let me introduce these 2 statements. First one is, it is impossible to construct a device that operates in a cycle and produces no effect other than the transfer or heat from a lower thermal energy and a lower temperature body to a higher temperature body. So that means heat transfers from high temperature to a low temperature. You cannot transfer heat from low temperature body to a higher temperature body without serving energy transfer by work. The second one is Kelvin-Planck statement. It is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. So the easiest way to understand this Kelvin-Planck statement, let's think about, we want to produce work. We want to produce mechanical work in a power plant by, by burning fossil fuel. So if you burn fossil fuel, you will create heat at high temperature. If you assume that there is a cycle that receives heat from a single reservoir to produce a net amount of work, that means there is no thermal energy left over after power conversion. The problem is, if you convert every thermal energy in this coffee to mechanical work, that means there is no thermal energy left over in the coffee. That means that the coffee is at 0 Kelvin minus 273 degrees Celsius, which is impossible because the Earth is maintained at a constant temperature. That is one example why we cannot produce work from a single reservoir. We need to reject heat to make a cycle, right? So these two are, one of the famous statements in thermodynamics in terms of the second law of thermodynamics. Then let's talk about reversible and irreversible processes. If we want to, make an ideal cycle, it is important to understand the difference between reversible and irreversible processes. Reversible process means a process that can be reversed without leaving any trace on the surrounding. What does it mean? If you buy a hot coffee like this and place this coffee on this desk, what's going to happen is that its temperature goes down because there's a heat transfer from this coffee to the surrounding air. This is irreversible process. There is no way, once the coffee is cooled down and magically coffee absorb heat from the surrounding air and become a hot coffee. That's not possible. So this is irreversible process. Then what is reversible process? One of the easiest way to understand the difference between reversible and irreversible process is to look at this pendulum. How this one works. We know how this pendulum works. It moves back and forth. So while doing so, the kinetic energy and potential energy exchange. So at this location, we have the maximum potential energy, and this potential energy is going to be converted to kinetic energy. That means that the velocity increases, and at the lowest point, we have the maximum kinetic energy, and this kinetic energy is going to be converted to potential energy. And at this location, we have the highest potential energy, and then this potential energy is going to be converted to kinetic energy. So this one moves back and forth. Then what's going to happen? After, the 2 hours, it will slow down and eventually stop in the middle, right? That is an irreversible process. Then why does it stop? If it is just, changing the energy from between kinetic energy and potential energy, why does it stop? Because while this pendulum is moving this way, the friction between the surface of this solid and the surrounding air is going to generate heat. That means kinetic energy is going to be converted to heat. So, you're losing energy. So that's why it's going to slow down, and eventually, when every kinetic energy is converted to heat, you stop in the middle. So it is an irreversible process. Then, what about if I put this pendulum inside the vacuum chamber? Then, is there any friction between the surface and the surrounding air? No. Then you can expect that this one is not going to stop. It will continue, move back and forth, right? This is irreversible process. So reversible process means that a process that can be reversed. And most processes in the real world are not reversible process. They are most likely irreversible process. However, not every irreversible process is the same. What about this one? When we have this pendulum in the air, how long it's going to take to stop? Maybe 10 minutes, 5 minutes, quite a long time. Now, if I put this, the pendulum in water, how long it's going to take? 2 seconds. Are they the same irreversible process? Not really. The one in the air is closer to a reversible process, and the one in water is far away from irreversible process. So even though you have the same irreversible process, one is close to reversible process, the other one is not. What about, the driving a car? Do you think a car is a reversible process? Not really. If it is reversible process, when you drive forward, you consume fuel. When you drive backward, you are producing fuel. That's not possible, right? Then we know that driving a car is a irreversible process. Now let's think about that you're driving, let's say, like a Prius hybrid car. You're driving hybrid car. And then next to you, someone is driving a dump truck. Okay? So, are they the same irreversible process? No, one is close to reversible process. One has higher gas mileage. That means that close to a reversible process. The other one, dump truck, has very low, the mileage. That means that it is far away from reversible process. So even though you have the same irreversible process, one can be close to reversible, the other can be far away from reversible. So if you can understand how irreversible it is, then you can, learn something from there. Let's think about this. There are two power plants. So there's a power plant. Power plants, power plant number 1 and power plant number 2. And let's assume that, I want to, work for, the power plant company. So that should be my first job. I want to produce electricity. Okay? So power plant number 1 is in Mount Pleasant. Mount Pleasant. And power plant number 2 is in Midland. So Midland is a bigger city than Mount Pleasant. So let's assume that it is the one in Mount Pleasant, the one in Midland produces like let's say 200 kilowatts of electric power. The one in Mount Pleasant can produce only 100 kilowatts. Then, when you want to, get a job in this power plant company, what do you want to do? Just a simple technician trying to, the maintenance, the how, each power plant works, or do you want to work for an R&D team trying to improve the efficiency of the power plant? So let's assume that since we are engineers, we want to, develop present power plant. So what is the efficiency of the power plant in Mount Pleasant? What is efficiency? What is efficiency means? It means that if you consume, let's say, this amount of, the fuel, how much electricity you can produce, right? So when you calculate, the efficiency, how you do that? Desired output, the power that you produces over required input, the fuel that you need to burn, right? So when you calculate the efficiency of the power plant in Mount Pleasant, it was 20%. Oh, that's pretty low. Then you calculate the efficiency of the power plant in Midland, it was 40%. Then you have no idea about about the very detail of how power plants are designed by just looking at the present efficiency. Which power plant has more room for improvement? So which power plant that will be easier to improve? One can simply say, okay, this one is only 20%. So there must be a lot of the stupid thing is going on. I can just go and inspect and then do a simple fix. I can increase this one from 20 to 22. Not a problem. But if you look at this one, 40% is pretty high. So maybe the power plant, the equipment there is going to be very well maintained and very well designed. So even though I spend, the years, I may not be able to increase only by 1%. That can be a reasonable guess, right? Right? Then, is that real? Not necessarily. What about if you can evaluate the efficiency of the ideal power plant cycle? If you can determine the ideal power plant cycle. So let's say that, now I know how to evaluate the maximum efficiency, the maximum possible efficiency for this power plant number 1. So this is a theoretical maximum. The efficiency in theory is 21%. And the efficiency in theory here is going to be 55%. And if you didn't know the theoretical efficiency, you can choose that. Okay, 20% is pretty low. So, the improving this one is going to be super easy. But now, if you know the maximum possible efficiency in theory, you can say this one is well developed. So there is not much room. If you choose this one to improve, it may take, the 50 years, and then you may increase 0.001%. But here, you have a large room for improvement. So if you pick this one, if you choose this one, the increasing the efficiency by 1% or 2% would be easier than this one, right? So from now on in chapter 5, we are going to study how to determine the maximum possible efficiency. In other words, ideal efficiency. Okay? So that's what we are going to do. Then, how can we, determine the maximum possible efficiency? It's very simple. There are reversible processes and irreversible processes. So if we can assume that every process in this power plant is reversible, that's when this power plant has the highest possible efficiency, right? So our assumption is going to be every process is reversible, and let's determine the efficiency, again. That's how we determine the theoretical maximum efficiency. Okay? So theoretical ideal cycle is called Carnot cycle. And in this Carnot cycle, we assume that every process in the cycle is going to be reversible. By that assumption, we can calculate its efficiency. When you calculate the efficiency of reversible process, that is going to be the highest possible efficiency. Okay? And how can we do that? Before we talk about, how do we, study Carnot cycle, let's learn about, some principles of Carnot cycle. The efficiency of an irreversible heat engine is always less than the efficiency of reversible one, because the reversible one is going to be the ideal system. And the efficiencies of all reversible heat engines operating between the two same thermodynamic reservoirs are the same. And let's study how to determine the efficiencies of Carnot cycle. It's actually pretty simple. We studied 3 cycles. The first one is heat engine. And the second one is refrigerator. The third one is heat pump. And how did we, evaluate the performance of each cycle? For heat engine, we used efficiency. The efficiency can be determined by desired output. What is the desired output? We want to produce power, W dot net. And what is required input? The heat that we need to provide, Q dot H. By the way, according to the energy balance equation, W dot net is always Q dot H minus Q dot L. So we can rewrite this Q dot H minus Q dot L over Q dot H. Then this one can be rewritten as 1 minus Q dot L over Q dot H. So this is the efficiency of a heat engine that we know. What about refrigeration system? We can use a COP. COP of refrigerator can be determined by the desired output, the heat transfer from refrigerated space, Q dot L, divided by required input, W dot net. By the way, W dot net is Q dot H minus Q dot L, so we can say COP of refrigerator can be determined by Q dot L over Q dot H minus Q dot L. Yeah, we know that. We studied that, today and also last week. What about heat pump? COP of heat pump can be determined by desired output. Why do we run a heat pump? To heat inside, Q dot H. And to make that happen, to heat inside, what we need to sacrifice? The mechanical power. Then COP of heat pump can be determined by Q dot H over Q dot H minus Q dot F. So these three equations are ways we evaluate their performances. Now let's assume that everything is reversible, which means Carnot cycle, Carnot heat engine, Carnot refrigeration cycle, Carnot heat pump cycle. Then how can we determine the efficiency? Since it is reversible, I'm going to say the efficiency of reversible heat engine, which is the maximum possible efficiency, can be determined by, everything is the same, but we are going to replace Q with temperature T. 1 minus TL over TH. So that is the maximum possible efficiency. What about COP? COP of refrigeration cycle, and this cycle is completely reversible. Then TL over TH minus TL. What about COP of heat pump? TH over TH minus TL. So this is how we determine the maximum efficiency, maximum COP. So this one slide has all the equations that you need in chapter 5. There's one thing you need to be careful here is when you look at this temperature, you need to make sure that the what temperature unit you have to use. Always Kelvin. So that's everything about the theory part of chapter 5. So let's solve a few problems together. Yes. Or this Kelvin for everything. Yeah. So when you have a heat engine to produce power, this is how you determine its the performance. The efficiency of an actual heat engine can be determined by this one. Then what is the maximum possible the efficiency? Use this one. So this one should be always greater than this one. And when your system is the ideal heat engine, then this efficiency should be the same as this efficiency. Okay? And based on that, let's solve this problem together. From a work production perspective, which means that if you design a heat engine, if you design a power plant in two locations, one where we can provide heat at 675 Kelvin and we can provide coolant at 325 Kelvin. The difference is 350. That's one location. Could be somewhere in the southern area. And the other, the location, the other, the alternative location where we can, build a power plant. At this time, the heat can be provided at 625, and the coolant is provided at 275. Still, the same temperature difference, 350, but at lower temperature, both of them. So, could be the northern region. So, which one has higher efficiency? Even though they have the same temperature difference, 350, 350. Then you can calculate the efficiency, the theoretical efficiency. Can be determined by 1 minus TL over TH. So the first location, A, the efficiency can be determined by 1 minus 325 Kelvin divided by 675 Kelvin. And the second location, the reversible efficiency can be determined by 1 minus 275 Kelvin divided by 625 Kelvin. So the maximum possible efficiency is going to be 0.519, which is 51.9%. And the other one is 0.56. In other words, 56%. So even though, each system shares the same temperature difference between, the high temperature thermal energy reservoir and low temperature thermal energy reservoir, so the difference is 350. The difference is 350. The second location can have higher efficiency because of the temperature difference. So based on only the temperature information, you can choose building a power plant in the second location would give you higher efficiency because it has a higher potential. Very easy to solve, right? And let's look at the second problem. A heat engine operates on a Carnot cycle. That means that you have a heat engine, you have a power plant that is an ideal power plant. And it has a thermal efficiency of 75%. Pretty high. 75%. That is the maximum possible value. If you assume that every process in the heat engine is completely reversible, then you can achieve that value. In reality, the actual efficiency should be less than that, right? The waste heat from this heat engine is rejected to a nearby lake at 15 degrees Celsius at the rate of 14 kilowatts. Determine the power output of the engine and the temperature of the source. Okay, we can do that. So the actual efficiency of a heat engine can be determined by W dot net over Q dot H. And since W dot net is the same as Q dot H minus Q dot F, it's going to be 1 minus Q dot L over Q dot H. And wait, it is the ideal heat engine. It is on a Carnot cycle. So you can say this is also the same as reversible heat engine efficiency, which is 1 minus TL over TH. So heat rejection, and the efficiency is going to be 75%. The heat rejection is 14 kilowatt, and this is the heat rejection, 14 kilowatt. Then, since the whole thing is going to be 0.75, you can determine Q dot H. Yes, Q dot H is going to be 56 kilowatt. Then what is the power output? According to the energy balance equation, W dot net is going to be Q dot H minus Q dot F. And this one is 14. This one is 56. So what is the power output? 42 kilowatt. So this much power can be developed by this heat engine. Then, what is the temperature of the low temperature thermal energy reservoir? 15 degrees Celsius. So that's TR. So this one is 15 degrees Celsius. Then 1 minus 15 over TH is going to be 0.75. So you can determine TH. Am I right? No, because you have to use Kelvin. 288 Kelvin. Then what is TH? 1152 Kelvin. That is TH. So that's how you determine the temperature of the source. Any question? So it's not that hard, right? Easy. Carnot cycle is very easy. We have 2 more problems, and that will be all for this chapter. We can do that. Two more problems. Okay, so we have a heat pump operates on a Carnot heat pump cycle. So that's an ideal heat pump. COP should be pretty high because in the ideal system. So we have a heat pump that transfers heat from low temperature to high temperature for the amount of Q dot L, Q dot H. To make that happen, we need to provide work W dot net. Then we have 2 equations. The energy balance equation is W dot net is going to be Q dot H minus Q dot L, and the COP of this heat pump can be determined by desired output. Why do we run a heat pump? Because we want to provide heat to inside. So Q dot H is desired output. And to make that happen, what is the required input? W dot net. And W dot net is Q dot H minus Q dot L. So we can say COP can be determined by this equation. By the way, it says that this is working on a Carnot efficiency. So it's an ideal heat engine. Okay, so this is an ideal heat engine. So we can determine COP of heat pump, which is reversible, can be determined by TH over TH minus TL, and they should be the same. So this is the theory. Let's solve this problem. COP is 8.7. Okay, so this one is 8.7. This one is also 8.7. And it keeps our space at 26 degrees Celsius. That is the temperature of the inside. So the indoor temperature is 26. So this one is 26. Right? Now we need to use Kelvin. 299 Kelvin. 299 Kelvin. And it consumes 4.25 kilowatt. So this one is 4.25 kilowatt. We want to determine the temperature of the reservoir from which the heat is absorbed, which is the temperature of the outside. How can we do that? So this one is 8.7. We have everything but TL. Can you determine TL? Yes. 264.6 Kelvin. So that's the temperature outside. What about the temperature, the heating load provided by the pump? So that is Q dot H. So this one is 8.7. 8.7 times 4.25. So Q dot H is going to be 37 kilowatt. So that's pretty good. We are only spending 4.25 kilowatt of electric power, and we can provide 37 kilowatt of heat into the house. That's how heat pump works. Any question? It's too easy, right? The last one, we have a heat engine receives heat from a reservoir at 900 degrees Celsius at a rate of 800 kilojoule per minute. So we have a heat engine. We have heat engine. What heat engine does? It absorbs heat from high temperature and produce work, W net, and reject any waste heat to low temperature, which is outside. The rate of heat transfer is going to be Q dot H, Q dot R, and we can produce W dot net. And the temperature of the source is 900. So this TH is going to be 900 degrees Celsius, right? Now we use Kelvin. 1173 Kelvin. And the rate of heat transfer is 800. So this Q dot H is 800 kilojoule per minute. And we reject heat to the ambient air at 27 degrees Celsius. That's the temperature of the heat sink. So 27, but we want to use Kelvin, so 300 Kelvin. And this is a Carnot heat engine. So that's an idea, reversible. And this work, the entire work output of this heat engine is used to drive a refrigerator, okay, so refrigerator, so there's a refrigerator is coupled. And what refrigerator does? It absorbs heat from low temperature and reject heat to high temperature, which is against the second law of thermodynamics. So we need to provide power. The rate of heat transfer is going to be Q dot L from low temperature, Q dot H to the high temperature. The temperature of the refrigerated space is -5. -5. So the temperature TR is going to be -5 degrees Celsius, which is 268 Kelvin. And transfer heat, this heat from the refrigerated space to the same ambient air at 27. So the temperature outside is 300 Kelvin. Determine the maximum rate of heat removal from the refrigerated space. So it says maximum. When can we, observe heat at the maximum rate? When this refrigerator is a Carnot refrigerator, which is reversible. So our assumption is going to be, this one is also reversible because it says maximum. So we want to determine Q dot R and for the rate of heat rejection to the ambient air. So what are they? This one, heat rejection to the ambient air. This one, heat rejection to the ambient air. So that's what we want to do. Kind of complicated, right? So let's talk about this heat engine first. We know that this is a reversible heat engine. So if you want to determine its efficiency, you can first use desired output, W dot net, over required input, Q dot H. And this is an ideal heat engine. So we can determine this by reversible efficiency, which is 1 minus TR over TH. So what is TH? 1173. What is TR? 300. So what is the efficiency? 0.744. What is the heat transfer rate from high temperature thermal energy reservoir? 800 kilojoule per minute. So can you determine the net power that we develop? Yes, we can. That is 595.2 kilojoule per minute. So that is the power output, 595.2 kilojoule per minute. Then what is the heat rejection from this heat engine? 800 minus 595.2. So the heat rejection, this one, is going to be 204.8. kilojoule per minute. So that's the heat rejection from this heat engine. Okay. Okay, then let's talk about the refrigerator. We know the temperatures at the low temperature reservoir and the high temperature reservoir, so we can determine COP. COP of refrigerator can be determined by desired output. What is desired output? Q dot L. What is required input? W dot net. And this can be determined by reversible refrigerator. COP of R, but this time it is reversible. How can we determine that? TR over TH minus TR. So what is TR? 268. 268. What is TH? 300. Can you determine COP? Yes. COP is 8.37. What is desired? What is the required input? W.net 595.2 kilojoule per minute. So what is the heat transfer from the refrigerated space? 4982. 4982 kilojoule per minute. So this one is 4982 kilojoule per minute. Then what is the heat rejection to the ambient air? This one plus this one. So Q dot H from the refrigerated refrigerator is going to be 5577.2 kilojoule per minute. So we are ready to determine everything. So the maximum rate of the heat removal from the refrigerated space, this one, 4982. The total rate of heat rejection to the ambient air, this one plus this one. That's how you solve this problem. So A is going to be this one, 4982 kilojoule per minute. Then what is the total heat rejection to the ambient air? This one is the heat rejection to the ambient air by the heat engine. This is the heat rejection by the refrigerator. So 5577.2 plus 204.8, which is 5782 kilojoule per minute. That's how you solve these problems. And that's everything about chapter 5. So you have a new homework assignment due a week from today, next Tuesday, chapter 5. Any question? No? Then see you on Thursday. I'm pretty sure that you are very disappointed about the difficulty of this chapter 5. So don't worry about that. We are going to study entropy, the hardest chapter of thermodynamics, starting from this Thursday. So you must be very excited this Thursday. See you on Thursday.